Alrighty guys, let's get ready for lesson 3.4, related rates. Now, this is, I feel like, the first time we're really getting into some actual AP style questions. Like when we get down to some of these story problems and stuff. Related rates is a really big concept. On the AP test, there's a lot of different things that they can ask about that, okay? Okay, so the idea of a related rate problem is to find a rate of change, usually with respect to time, okay, of one quantity by using a rate of change of the related quantity. So that's what they call related rates. Two things are related to each other, okay? And when we find rates of change, we're looking at derivatives. And notice how it says with respect to time. So we're going to use, kind of shows you right here, we're going to be taking derivatives a lot of times with respect to the letter t, all right? Because that's going to stand for time. Okay, so the first step, draw a figure if necessary. Like any type of word problem, if it's not drawn for you, absolutely you got to draw a figure. Okay, sometimes I get a little crazy with my figures. It's kind of fun. All right, got to draw a figure, choose all your variables. Write what is given, so read through the problem, write what's given and what you're looking for using all the variables and the dt. Okay, we'll talk about that. Write an equation relating the variables. Now, this is really important. If something is changing, it has to be represented with a variable. If something is constant, it has to be represented with a number. I'll give you a very simple example. We'll probably see this exact problem, I'm sure. You guys have seen this question in trigonometry as well. Okay, let me draw it up here. We have a ladder leaning against a wall. In trig, what you would do is like, how tall is the ladder? Where is it touching the wall based on the angle and stuff like that, right? Well, now what we're going to do is the ladder is going to slide down the wall, okay? Okay, and so within this movement, you guys, I don't really know if I can like make this happen, kind of. Oh, look at that, woo. Okay, so the ladder with the guy is sliding down the wall and sliding across that thing or whatever. All right, so that's very typical. Well, when I go to set my stuff up, what I have to ask myself is like, is this side changing as the ladder sliding down the wall? Well, yeah, because it's going out that way. It's getting bigger. So this one is changing. I need a variable for that. Is this side over here changing? Yeah, is it going down the wall? This side is also changing. But is the ladder changing? No, like we don't have a ladder that's magically growing bigger. This side is constant. So we want to make sure we use a number for that and not a letter, because when we start taking derivatives, we need to know the difference between if it's a number and a letter. Okay? All right, cool. Look for secondary relationships. It's a little tricky, but we'll talk about that with a specific cone problem if we can find that one. And then implicitly, so we did this yesterday, right? Implicitly differentiate both sides with respect to time, substitute and solve. Okay, here we go. Let's go through our steps here. In this problem, the first three steps of the procedure are done. So let's say they gave us something, we set up an equation, we're all good. It's having us kind of jump to the end. We only have to complete the last two steps. Okay, so it's given. So we find dx dt. That's the derivative that x is changing at with respect to time. We have y is 4, and then my equation is xy equals 12. Find dy dt. Okay? Cool. So let's go ahead and take the implicit derivative of this. Now, tiny little bit of a pain, guys, because guess what we got to do? Product rule. Okay? So product rule is going to go like this. Derivative of the first, which is 1. But remember, we're not taking the derivative with respect to x. We're taking it with respect to t. So it's 1 dx dt times the second. Okay? So let's see if I make this clear. The derivative of x is 1 dx dt times the second, and then the first, and then derivative of the second. All right? The derivative of y is 1 dy dt. And that equals, I almost wrote 12, big mistake, that equals 0. because the derivative of a constant is 0. Okay? So if you guys see that product rule and you get the dx dt, dy dt. And now I'm trying to find dy dt. I'm trying to find that. So cool, let's just sub everything in. We don't need our 1s anymore. Dx dt is -6. Y is 4. Shoot, it didn't tell me what x is, and I'm supposed to find dy dt. Okay, if it didn't tell me what x is, how might I find that? Well, let's look back up here real quick. And it just gave me some information. It said y is 4 and x times y is 12. So what do we think x is, right? If I, don't have one of my variables, I can plug this in. X times 4 equals 12. Well, it looks like x is going to be 3. Okay? So right here, I have -24 plus 3 dy dt is 0. Add the 24 to both sides and divide by 3. Okay, dy dt is 8. All right? Now this one wasn't in the context of a problem, so that's okay. This is in the context of a problem, though. Let's check it out. A windlass is used to tow a boat to a dock. The heck is a windlass? Does anybody know what a windlass is? I'm looking it up. Looking it up, guys, because this is what I do. Windlass. Huh. It's like a winch, right? That's a windlass. Okay, whatever. All right. A windlass is used to tow a boat to the dock. The rope is attached to the boat at a point 15 feet below the level of the windlass. If the windlass pulls on the rope at a rate of 30, what rate is the boat approaching the dock when there's 25 feet of road out? By the meaning of the answer. There's so much going on. Okay, first, you got to understand the problem. All right, so check it out. Here's my boat. I'm going to do this so I can kind of make my boat move a little bit. Okay, check this out. This is pulling the boat in, and the boat is being pulled in. You guys see that? So it's like there's this little windlass pulley thing up here, I guess, or whatever. And as it pulls, but like gravity is keeping the boat on the ground. Okay? So look, let's say we call this triangle like XYZ, right? Say we call this XYZ. Well, X, definitely changing. The boat's getting closer to the dock. Z, the rope is definitely getting shorter. That distance is not changing, okay? You guys see that? As I move my boat through here, that 15, even to where I get it to right there, is not changing. All right, so that side is constant. Okay? The rope is attached to the point 15. They labeled that for us. That was nice. If it pulls in the rope at a rate of, okay, the rope is getting shorter, right? It's pulling it in at a rate of 30 feet per minute. The rope I called Z. So you know what that 30 feet per minute is? Can you guys guess what variable that is? That's dz dt. Okay. Now you might want to argue like, okay, it's pulling it in and it's getting smaller. So we could do like negative. That's not really going to matter. It's because the other side's going to be negative too. Let's just go ahead and call it 30 feet per minute. At what rate is the boat approaching the dock? Okay, check this out. Now this is going this way. dx dt is what we're trying to find. How fast is the boat going? Because the thing that's pulling it is going at one speed and the boat is going at another speed. All right, so we kind of got this set up. And then it says, when there is 25 feet of rope out. Okay, when there's 25 feet of rope means when Z is 25. All right? Okay, so first we have to find an equation that's going to relate all these things together. Guys, I'm using a right triangle, and I have lengths of sides. What equation do you think of when you think of a right triangle? A squared plus B squared equals C squared. Okay, so there's certain equations. This is a very, very typical one. We're going to use Pythagorean Theorem. All right, so A squared plus B squared equals C squared. So I'm going to write X squared plus 15 squared equals Z squared. So notice I didn't use another letter for the 15 because it's constant. I just used 15. X squared plus 15 squared is Z squared. X and Z are changing. So as I take the derivative here, this becomes 2x. And then because I'm taking the derivative with respect to time, dx dt. All right, cool. 15 squared is 225, but the derivative of that is 0. So that's going to actually go away. And then it's going to equal 2z dz dt. Perfect. Now we're going to start plugging stuff in. Okay. X, I don't have x. Dx dt is what I'm looking for. I have z is 25. And dz dt is 30. Okay? I didn't have an x though. Is there somewhere I could go back and find that x? Well, let's look in here. Let's bring the 15 squared back. Z is 25. So if I were to plug that in, you guys, x squared plus 15 squared equals 25 squared. Because this says at the point when there's 25 feet of rope. All right? Now, usually, especially if this is a no calculator question, you guys, it's going to give you a triple. Hopefully you guys remember all your triples, okay? As a reminder, your Pythagorean triples are like 3, 4, 5, 6, 8, 10, 5, 12, 13, 7, 24, 25. These are the most common ones. This is a 3, 4, 5 triple, okay? It's just a multiple of it. So the 3, 4, 5 triple is, if I multiply it by 5, it's 15, 20, 25, okay? Which means x is 20, 15, 20, 25, right? If you're not allowed to use a calculator, it's not going to expect you to do those calculations in your head. It's going to give you a triple. Cool. So now I can come back over here. I can say, oh, x was 20. And so I have 40 dx dt. Let's see, 50 times 30 is 1500. If I divide that over 1500 divided by 40, do I need to simplify that? Absolutely not. This is a free response test. As soon as we solve for dx dt, we're done. And we write a sentence explaining the meaning of the answer. So the first thing I like to do is I like to look at units. If that was feet per minute, this is also feet per minute, because each of the sides is feet, right? So the boat is moving toward the dock at a rate of 1500 over 40 feet per minute. Do we have to write that? Yeah, we do. Because a lot of times getting the number is not the answer we're looking for, it's the explanation. So a lot of times on an AP question, it'll say, explain your answer in context. So there's two things that you'll see at the end, right, of a sentence. Explain, or like this says, write a sentence explaining the meaning of the answer. So they'll say, explain your answer within the context of the problem. What did you just find? Or they'll say, like, justify your answer. These always have explain your answer. Okay? Cool. We ready to try another one? All right, y'all. Here we go. The funnest stuff ever. Related rates word problems. These are so dope. Okay? All right, here we go. First things first. We need a picture. A policeman traveling south towards an intersection. He's going to be a motorcycle cop, I think. Because I don't want to drop a cop car. Okay, here we go. He is traveling south toward the intersection. Spots a speeding car traveling east away from the intersection. This is Mitchell. Mitchell is speeding. Bad Mitchell. Okay? Whoa. That was weird. Okay. So I got my picture, right? This is the Popo. This is Mitchell. Okay? Spots a speeding truck around the east. Okay. When the policeman is 0.6 miles from the intersection and the car is 0.8 miles from the intersection, the policeman's radar shows the distance between them is increasing at a rate of 20 miles per hour. That means that this is a derivative. So you guys, I need to get some letters now. I can use A, B, C, X, Y, Z. Doesn't really matter. Let me go ahead and use A, B, C. So the rate at which this is changing, we're going to call that dc dt. It's the rate at which the distance between them at the same time, all right, is changing. If the speed of the police car, so that's over here, dA dt is 60 miles per hour, what is the speed of the car? We're trying to see how fast is Mitchell going. All right? Okay, so I got all my information down. And then write a sentence explaining the meaning. Okay, I want you guys to think about this. So, here's the policeman driving his little motorcycle, okay? And here's me in my minivan. Let's go. Okay? He is approaching there. I am going that way. Those two are changing. Guess what? So is the distance between us. Because as he gets here and I get there, that distance is not staying constant. Okay? So all three sides are variables. None of them are constants. All three sides are variables. So again, with right triangles, almost always we use a squared plus b squared equals c squared. Okay? A squared plus b squared is c squared. So here's my derivative. 2a dA dt, 2b dB dt equals 2c dC dt. And I start plugging stuff in. All right? A is 0.6, dA dt is 60. Okay, now there's actually something that we need to talk about with this. As the popo is getting closer to the intersection, this distance is getting smaller, right? Because he's coming closer and closer and closer. What that tells me is this is actually a negative rate. Okay, not because he's like slowing down or whatever, but because he's shortening the distance, whereas this is going to be a positive rate. Okay, so I actually need to remember to put a negative 60 in there. And that's something you got to be a little careful of, is thinking about is making it bigger or smaller, okay? All right, 2b is 0.8, dB dt is what we're trying to find. And then 2c dC dt, okay? We don't have c yet. We didn't have that yet. And so when you guys look at this, especially if it were a no calculator question, even if not, like, they usually try to use triples in right triangles, okay? And this is a multiple of the 3, 4, 5 triple. This is a 6, 8, 10 triple. So if it's 0.6, 0.8, C is going to be 1.0. All right, and that's what I'm going to use right here. Okay, so I get 2 times 0.6 times negative 60. I get negative 72. 1.6 dB dt equals 2 times 1, 2 dC. Oh, I didn't even put in my dC dt. Whoops, whoops, whoops. I know what dC dt is. It told me right here. dC dt was 20, so equals 40. As I add the 72 over, I get 112 divided by 1.6. Ooh, let's see how fast Mitchell is going. 112 divided by 1.6. Aw, heck no, that's not even speeding. I got 70, okay, miles per hour. All right? So, write a sentence explaining the meaning of the answer. Ms. Mitchell, or this just says the car, the speed of the car is 70 miles per hour. Okay, there you go. All right, and that had 3 different sides changing, but we were still able to tackle that. All right, now, this is a... Well, actually, I feel like maybe I want to do one more related rates problem before we look at the cone one. Let's see here. Okay, so I want to do one more with you guys. We're going to do one off the homework. We won't totally have time in class. Before I do the cone one, I want to do number 5 off the homework, okay? All right, we have a cube. Now, because it's a cube, all sides are the same. So can I go ahead and call that like x, x, x? All right? All of the edges are expanding, getting bigger at a rate of 2 inches per second. So what does that represent? Dx dt, and it's positive because they're all growing at a rate of 2. Okay, and then it says at the instant, so they started small and they're getting bigger and bigger and bigger. If I took a snapshot when each of the edges is 5. Okay? Find the rate of change of the surface area, find the rate of change of the volume. If it says rate of change of surface area, it's d surface area dt. Rate of change of the volume is dv dt. Before I can find those, I need formulas for those. Let's find a formula for surface area. Let's see. That's x squared. That's x squared. That's x squared. There's 6 sides. So the surface area of a cube is just 6x squared. Okay? So let's take the derivative of that, d surface area with respect to t. And I'm going to go ahead and take the derivative of 6x squared. When I bring that down, that's going to give me 12x dx dt. It said at the instant that x was 5, and they're expanding at a rate of 2. So that's going to give me 12 times 5 times 2, 120. Now, in order to find the units, right, we got to figure out what the units would be of surface area and what the units would be of time. This is telling me that it's inches per second. Well, once I switch to surface area, that's a 2-dimensional thing, guys. That's going to be inches squared. That's what surface area would be per second. Okay? And it says to write a sentence explaining it. So the surface area of the cube is expanding or increasing or whatever by 120 inches squared per second. Okay, now I'm going to do the same thing, but I'm going to do it with the volume. Now we know that for a cube, the volume is just base times width times height, so the volume is just x to the third. So I need to find dv dt, the rate at which the volume is changing with respect to time as this cube is blowing. Okay, it's growing. I was thinking about holding it as the cube is growing. All right? 3x squared dx dt. So it gives me 3. X is 5. And it's changing at a rate of 2. So dv dt is going to give me 5 squared is 25. So 50 times 3 is 150. Now, what are my units here? Well, volume is a 3-dimensional thing. So this is going to be inches cubed per second. And my sentence would be the volume of the cube is expanding or increasing or whatever by 150 inches cubed per second. Okay? So that's pretty much all we're doing. So let's go back now and look at this cone question. All right, and when you guys see a cone, you might be like, okay, we got to figure this out. All right. I don't love that picture. I'm going to draw myself a picture. Gravel is falling on a conical cone. On a conical pile. I said conical cone. That's funny. At the rate of 10 feet cubed per minute. So I need a letter for that. I need to figure out what that is. Guys, a lot of times your units will tell you the letter. Feet cubed, what do we use units cubed for? So typically we use units cubed for volume. Now if it just said 10 feet cubed, that's a volume thing. But then it says per minute, that's a dv dt, that's a rate. Okay? At all times, the radius is twice the height of the cone. Okay, so as it's falling, okay, here's the height, here's the radius. So at all times, radius is twice the height of the cone. All right, find the rate of change of the height of the pile. What am I looking for? When it says find, I want you guys to write that down. Rate of change, that means it's going to be a d something dt, of the height. So that's what I'm looking for, dh dt. When the radius is 6. And then it gives me the formula for a cone. Right? It's explaining the meaning of the answer. All right, you guys, now look. Okay. Could I take the derivative of this so that I have dv dt and use a product rule? You certainly can. You can definitely do that. I'm going to show you a couple of different ways to do this, I think. Okay. dv dt is 1/3 pi. Okay, and then in here, I'm going to go ahead and I just put the 1/3 pi out front so I don't have to mess with it. Derivative of the first times the second plus first derivative of the second. Okay? Now this is a little bit crazy, this equation, but let's go ahead and see what we can plug in. All right, it told me that dv dt was 10. It told me right here r is 6. It did not tell me dr dt. I need to find that. It did not tell me yet h. And then r squared. And then dh dt is what I'm looking for. So you guys, I don't have a dr dt and I don't have an h. Well, let's see here. Why did they tell us this piece of information? When r is 6, what's h? H is 3. So when r is 6, h is 3. And then how do I find dr dt? Well, let's take this and let's take a derivative of it with respect to time. Dr dt equals 2 dh dt. All right? So what I could actually do right here for dr dt is plug in 2 dh dt, because I don't know what dh dt is. But now, at least I'm only solving for one variable. Okay? So look, I have 1/3 pi, 2 times 6 times 2 times 3. Okay, so that's 12. Times 2 is 24. Times 3 is 72. 6 squared, that's 36. If I add those together, 108. 108 divided by 3 is, you don't have to necessarily do all this simplifying, but it's going to be 36. And so I end up with dh dt equals 10 over 36 pi. And this would be units of whatever dr dt was, feet per minute. Now, can you guys agree that the product rule, this was like not great. This was like a little bit of a pain, okay? Let me show you a different way to do it and see if we get the same answer. All right, check it out. Let's take this equation. Let's move over here. Now, we're trying to find dh dt. So what would you guys think if I got this all in terms of h? See how we have r equals 2h right here? Before I even take a derivative, let's plug that in. 2h squared h. Okay? Let's plug that in before I even take a derivative. All right, 2h squared is 4h squared. So my volume is 4/3 pi and then h to the third. Okay, so I just did a little bit of manipulation so I don't have so many variables. Why does that help? Well, now I don't have to do freaking, what's it called? Product rule anymore. Okay? Here's my derivative. dv dt equals, bring that down in front. 4/3 times 3 is 4 pi h squared dh dt. I already knew that dv dt, because that gave it to me in the beginning, was 10. And then, I don't know what h is, but the same thing when r is 6, if I plug it in, h is 3. So I get 10 equals 9 times 4, 36 pi dh dt. So dh dt is 10 over 36 pi feet per minute. So same thing, okay? But it's a little bit easier if you can eliminate variables at the beginning. So that's definitely one of the things that we're going to be talking about, okay? Shoot, guys. Hopefully you understood that. It's a little tricky, but we're going to go over it in class. All right? Peace out, my friends.